enough time to complete the defense. That's the most important thing. So
Yeah.
we are all ears.
Yeah. So can you see my screen clearly and the laser pointer?
Yes.
Okay. So good morning, everyone. My thesis defense is entitled on the co-design of electronics and photonics for optical communication. Sorry. Here's the outline of my presentation. First, I'll begin with the motivation and background. Then I'll talk about my 3 research objectives and their outcome. Following that, conclusion, future work, publications, and finally, acknowledgement. So over the past 5 years, data traffic tripled from 4.7 in 2015 to 15.3 in 2020. And if we look at breakdown of this data traffic, we find that 77% is within data center. To support this increase, to support this data traffic in data center, electrical interconnects are being replaced with optical interconnects. That in turn creates a demand for high sensitivity, high speed, power efficient optical receivers. To support the development of these optical receivers, it's possible to leverage the silicon photonics technology. And in silicon photonics technology, it's possible to leverage components such as grating couplers, optical delay lines, directional couplers, to pre-process light or to manipulate the optical signal before it's applied to the electronic part of the optical receiver. This creates opportunities to design receivers with reduced cost, reduced chip area, and better energy efficiency. And this is the focus of my thesis, is this the co-design aspect. And there are 2 subtopics that fall under this co-design aspect. The first is exploiting silicon photonics in the design of optical receivers. So I have designed 3 chips. I'll present 2 designs here. And the second subcategory or subtopic is the design of passives in the silicon photonics platform. And what I mean by passives are components such as inductors, capacitors, or antennas that are usually located on the IC side. So this subtopic tries to relocate these passives from the IC side to the photonics side. I have designed 3 chips, but I will only present 1 design. So the first research topic is a receiver that attempts to replace a clock phase generation circuits from the IC side optically. So using optics to replace clock phase generation circuits. So conventional optical receiver consists of a photodetector at the input that converts the optical signal into photocurrent, followed by a transimpedance amplifier that converts this photocurrent into voltage. Following that, there are some voltage amplification stages that amplifies this voltage signal. And then there are usually latches that acts as an analog to digital converter. And usually there are several latches. In this case, 4 latches. And these 4 latches are clocked by 4 clock phases. And this is done for 2 reasons. It allows more time for the latch to make a decision based on the incoming bits. So that's the first advantage. And the second advantage is that in a lot of situations, it's desirable to have a separate or demultiplexed output. And this scheme or this having several latches allows us to have that. And this is the basic functionality. Say we have 9 data bits coming, then phase 0 will sample bit 0, phase 90 will sample bit 1, phase 180 will sample bit 2, phase 270 will sample bit 3, and then again phase 0 will sample bit 4, and so on and so forth. And this way we can obtain a demultiplexed output. However, to do this, we would need to have a clock phase generation circuit to generate the clock phases, and we also need duty cycle and quadrature detection and correction circuits. And these circuits are used to ensure that the clock phases have the proper duty cycle and they are indeed in quadrature and that they have the proper phase shift. The challenge, however, is that these circuits, they tend to be power hungry and they tend to be complicated to design. So the proposed idea, why not split the input signal optically and then delay each of the 4 outputs by 1 bit relative to the previous one. And then this way we can use 1 clock phases to sample 4 bits in one time. And this way we do not need these clock phase generation circuits or the other complicated circuits, such as the duty cycle and quadrature detection and correction circuits. And we still can obtain the demultiplexed output, as you can see here. And this is done with this silicon photonic structure. In this structure, the optical signal is coupled to the silicon photonic chip using a grating coupler. And the optical structure, what it does, it splits the signal into 4, where the first output undergoes no delay. the second output undergoes 1 bit delay, the third output undergoes 2 bits delay, and finally the fourth output undergoes 3 bits delay. So we use optical delay lines. At the same time, we use directional couplers to ensure that the optical signal, the strength of the optical power at each of the 4 outputs is the same. So maintain the same power at all of the 4 outputs. Then each of the 4 outputs is coupled to a photodetector that is connected to a sub-receiver. So we have 4 sub-receivers on the IC side. And in this way, silicon photonics were used to replace clock phase generation circuits. So this is the circuit implementation of one of the 4 sub-receivers. It consists of a common gate TIA that converts the photocurrent into voltage. Following that, there are 2 cascade voltage gain stages that amplifies this voltage. Then there is a CML latch, a pseudo NMOS inverter, and a D flip-flop that acts as an analog to digital converter. And finally, there is the driver stages that drives the measurement equipment. Here's the experimental validation of this receiver. This receiver was measured at 12.5 gigabits per second, so that's the input data rate. And here we show the 4 sub-rate outputs at 3.125 gigabits per second. Here's the macro graph of the chip, the fabricated chip. And this receiver achieves a sensitivity of -4 dBm. And it was fabricated in the 65 nanometer CMOS technology node. And we noticed that the clock power consumption percentage is around 10% of the total power consumption of the receiver. And this is compared to somewhere between 30 and 45% found in the literature. And this shows that it's feasible to use that silicon photonics to reduce power consumption of optical receivers. And this receiver was published in the IEEE Transaction on Circuits and Systems 2 Express Briefs. So the second topic of this presentation is an improved receiver that also uses what we call a low bandwidth front end to boost the speed of this receiver to 22 gigabits per second. So as I mentioned, this is a low bandwidth receiver. So I'll briefly introduce what's a low bandwidth system. So a conventional system, so this is the conventional optical receiver, as I mentioned, photodetector, a transimpedance amplifier, limiting amplifiers to boost the voltage, and finally some latches that act as an analog to digital converter. A conventional full bandwidth system is a receiver that has a bandwidth larger than 0.5 of the data rate, typically 0.7. So that's the design that people aim for when they design these receivers. So say that we have a 20 gigabits per second input data. So the bandwidth of the front end has to be 14 gigahertz. A bandwidth less than 0.5 of the data rate will result in intersimple interference. So that's why it's designed for a bandwidth above than 0.5 of the data rate. The problem, however, is that these in conventional systems, they are power hungry and they do not scale well with technology node. So if you move to more advanced technology node, they remain large in size. A low bandwidth system is a system that uses a front end with bandwidth less than 0.5 of the data rate. So why would we want to use a low bandwidth front end? Because it has a better signal to noise ratio, and this is because the bandwidth is limited. So there is less integrated noise within the bandwidth of the system. They promise smaller size, and they promise superior energy efficiency. So, but the challenge that comes with them is that we need to compensate for this bandwidth reduction, and we need to find a way to remove this intersimple interference. So this is the proposed design. And in this proposed design, the input is applied to a 1:4 optical splitter. It has 4 outputs. So the first output is not delayed. The second and third outputs are delayed by 1 bit. And the fourth output is not delayed. Then each of the 4 outputs is applied to one of 4 sub-receivers. And each sub-receiver consists of a photodetector that converts the optical signal into photocurrent. And then there is an integrating capacitor. And this capacitor will integrate for 2 bits. Following the integrating capacitor, there is a switch that resets the integrating capacitors for also 2-bit periods. So I'll get back to this slide. But let's look at this delta V, this integration voltage first. So this is based on the incoming bits, there are 4 possible combinations. Say that the 2 bits were 0, then we do not have any voltage. Say one of the bits is 1 and the second bit is 0, we get this kind of voltage because there is a photocurrent here, then the photocurrent drops to 0. So we get this kind of waveform. And then if we have 0, 1, then we get this kind of waveform. And finally, if we have 1, 1, we get this kind of waveform. And this is the reset. So the reset starts here as you can see, so it resets at this point. And if we overlap all of these 4 combinations on top of each other, we get this kind of eye diagram. This is what I call a triangular eye diagram. And here's where the power saving comes from. Because if you look at this eye diagram, the symbol rate is half the data rate. So we can relax the bandwidth of the next stages. And this is why we can save power consumption. So this delta V is then amplified using 2 voltage gain stages. And there are 2 CML latches that act as an analog digital converter. So they convert the analog voltage into a digital signal. Then there is a diff pair that amplifies this digital signal. And finally, there's a D flip-flops that 3 times the signal. And there's an XOR gate for decoding. And what I mean by decoding is that this pattern, Dn as the input, is actually an encoded pattern. And it's encoded in such a way that the first combination of 0, 0 is used to represent a 0. And the last combination of 1, 1 is also used to represent a 0. So 0 XOR with 0, it's 0. And 1 XOR with 1, it's 0 as well. And the second and third combinations are used to represent a 1. So if we XOR 1 with 0, we get 1. And if we XOR 0 with 1, we get 1. So this way, the decoding is done with an XOR gate. And this is how we get rid of inter-simple interference, through this encoding and decoding. And finally, there's the buffer that drives the measurement equipment. And here we show in this timing diagram, here we show that it's possible to recover all bits using this technique, using the delay lines and using only 2 clock phases. So here's the circuit implementation, the integrating capacitor at the input. Then we have an NMOS switch and the dummy PMOS switch used to implement the reset function. Then there is 2 cascade voltage gain stages that amplify the voltage. Then there is a master CML latch and a slave CML latch that act as an analog digital converter, diff pair to amplify the voltage, the D flip-flop for retiming, and the XOR gate for decoding, and finally the output buffer. So that's the circuit implementation of this receiver. Here's the experimental validation of this receiver. The light from the laser is applied to a polarization controller, then to a Mach Zehnder modulator to modulate the light, an EDFA to amplify the optical signal, a filter to get rid of any unwanted ASE noise. A VOA is then used to attenuate the optical signal as needed for bit error rate measurements. Then we use an optical delay line, and this delay line is just used to align data with the clock for proper sampling. So the clock applied here, this is just used to delay the data as needed for proper sampling. Then we have a 1090 splitter where 10% is applied to the power meter, and 90% is applied to the 1 to 4 splitter. And there are 4 delay lines that are used to delay the signal, as mentioned in the previous slide, as mentioned in the architecture. And finally, the chip. And the chip has 4 inputs and 4 outputs. Each of the 4 outputs is connected to a digital communication analyzer to capture the eye diagram and an error detector to do bit error rate measurements. Here's the macro graph of the fabricated chip. And this chip was measured at a speed of up to 22 gigabits per second. And here is the quarter rate output eye diagram at 5.5 gigabits per second. And this receiver was, so this receiver shows that if we use low bandwidth front end, then we can really boost the speed. So this was fabricated in the 65 nanometer technology node, and we still achieved a speed of 22 gigabits per second, which is a relatively high speed. And this was just recently published in the IEEE Journal of Solid State Circuits. So the third topic is the demonstration of inter-chip RF data transmission using on-chip antennas in the silicon photonics. So this falls under the second category of passives in the silicon photonics platform. And so recently we noticed that there was increased interest in the development of passives in the silicon photonics platform. As an example, our group developed an RC filter in the silicon photonics platform. This group from University of Ghent developed a matching network from a photodetector to an antenna that allows optimal power transfer. So following this trend, so we followed this trend, we saw that many people are gaining interest on this topic, but we also noticed the research gap is that people are designing people are designing photodetectors, high-powered photodetectors to drive antennas, and they are designing matching networks, but we didn't find an antenna in the silicon photonics platform. So we attempted to do that. We attempted to develop an antenna in the silicon photonics platform. And what motivated us to do this is that the silicon photonics has low substrate conductivity. And because it has a low substrate conductivity, it means that there is less RF power lost as heat within the substrate. And because of this, we do not need to do any post-processing, such as etching. We do not need to thin the substrate, which is usually done when the substrate conductivity is high. So that saves on costs, and it's a relatively cheap process compared to modern CMOS process. So here is the silicon photonics platform stack. It has 2 metal layers, and we use that to build the antenna. And it's a simple monopole antenna designed at 15 gigahertz. It consists of the ground plane, as you can see here, and then there is the antenna body. And in the antenna body, we have implemented small holes to pass the design rules check, so that we can fabricate the antenna. So there are design rules check, such as metal density width, metal density, and the metal width. So we had to pass these design rules. So we implemented the whole array within the antenna in order to be able to fabricate this chip. So to measure this chip, to measure these antenna, we used 2 antennas, we put them next to each other, and then we landed RF probes on these antennas, and we did S-parameter measurements. As you can see, there are good agreement between simulations and measurements with some shift. And this shift is because in the simulations, we did not model the body of the probe, which was complicated to model. We anticipated this problem. So what we did is we maintained symmetry in the measurement setup. So because we maintain symmetry in the measurement setup, any shift is applied to both antennas at the same time, and we were still able to measure the chip and demonstrate inter-chip RF data transmission. So here's the measurement setup or that we use to demonstrate inter-chip RF data transmission. So it's very similar. So this is a homodynamic transmission scheme. So we use a homodynamic transmission scheme. So it's very similar to the setup that I had shown in the previous slide. The only major differences are we use a mixer as well. So in order to modulate the Mach-Zehnder modulator, we mix the input data with the 15 gigahertz RF carrier. So there are 2 carriers. There's the RF carrier and there's the optical carrier. So, and the transmitting antenna is driven directly by a photodetector. And on the receiving antenna, we use another mixer for demodulation. So the demodulated signal is then amplified using an RF amplifier. And because this is a homodynamic transmission, we'll have a component at 30 gigahertz. So 15 on the transmitter side and 15 on the receiver side. So we use a low-pass filter to get rid of the component at 30 gigahertz. And the baseband signal is then applied to a sampling scope to capture the eye diagram and error detector for bit error rate measurements. And here we show that we were successfully able to demonstrate inter-chip RF data transmission. We captured the eye diagrams on the receiving side. So this is the first time we demonstrated that RF data transmission was demonstrated in silicon photonics using these antennas. And we think it might be feasible to also implement an integrated photodetector antenna emitters on the same chip. We did some feasibility study and we found that it might be feasible. So that might be an interesting future research direction. So this antenna demonstration was published in the IEEE Photonics Technology Letters. So in conclusion, in my research, I've developed for the first time a demultiplex by 4 optical receiver that uses silicon photonics to replace clock phase generation circuits. And as I mentioned, the power consumption percentage, we found out that it's 10% compared to 30 to 45% in the literature. We developed also, I participated in the development of a demultiplex by 2 optical receivers with superior energy efficiency. So this receiver actually achieves an energy efficiency of 156 femtojoule per bit. And this is the best energy efficiency to our knowledge. And this is because of the simplicity of the receiver. It's a simple receiver that consists of a TIA and a latch. So it's a very simple receiver. There is no clock generation circuits because of the silicon photonics. So we were able to achieve such a high energy efficiency. We demonstrated a 22 gigabits per second novel integrating front end, and we were able to achieve a high speed of 22 gigabits per second in the CMOS 65 nanometer technology node. I developed and demonstrated for the first time inter-chip RF data transmission in the silicon photonics platform. I also participated in the development of a moving average and a low-pass filter in the silicon photonics platform, demonstrating that it's feasible to have passives in the silicon photonics platform. So as a future work, I think it might be interesting to look into the monolithic design of the integrating front-end receiver, because I found that the sensitivity of the receiver heavily depends on the parasitics at the input. So if we have a monolithic design, then we can remove the POM pad at the input. And if we remove the POM pad, I think we can get a significant boost in sensitivity. The second topic that might be interesting is the development of clock and data recovery circuit for the low bandwidth receiver. So that's an interesting research direction. And also the development of a silicon photonics based delay locked loop where delay elements are implemented using optical delay lines. So this also might be an interesting research direction. And finally, as I mentioned, the development of integrated silicon photonic photodetector antenna emitters on the same chip. So in terms of publication, my PhD work has resulted in 12 publications, six accepted journal papers, and 6 accepted conference papers. Here is the list of my journal papers publication, and here is the list of my conference paper publications. And finally, I would like to acknowledge my advisor, Professor Odile Biron-Ladisau, and our group mentors. I would like also to thank the committee members, the examiners, and the thesis committee for their valued input. I would like also to thank my parents, wife, and friends for their support. Thank you very much. I'll be happy to take any questions you may have.
Well, thank you and congratulations on the job. Very well done. It's quite a challenge to summarize years of work in 20 minutes, and you did a really, really good job. Congratulations.
Thank you.
We will now turn to the oral committee defense member to ask questions. We'll start with Professor Wu.
Well, great. Thank you, Professor No. Well, the congratulations, Baha, for this, the excellent presentation and also the excellent work, and I can see which can be, reflecting through your publications, particularly the new publication from the Journal of Solid State. Okay, I think that's that's very, the high quality journal. Indeed, lots of interesting ideas presented during your, in your thesis and actually during your presentations. And same time, I have seen that particularly you have done lots of, interesting, let's say, work on this, through basically for this original contributions. But one of the things which actually I can see that what you want to do that you want to create the end-to-end in the digital domain, optical digital domain, okay, down to the end user. Then in something in between, you have a number of the analog parts. You have lots of analog parts, particularly the CMOS digital parts or the analog parts. And of course, that's will be the interesting combination, I would say. I want to ask you a few questions. Of course, before my questions here, well, there's a number of I will suggest you to go back to your thesis to correct a few points. For example, like a page, the thesis, I think 105. I will not say anything. There's something which is a little bit like you talk about frequency. Actually, you use dB. It's not dB. Frequency, not dB here, for example. Okay, figure 5.16. Okay, that's a frequency should be in your case here is a hertz. Okay, so I just point out there's some typo there, and of course there's page 29. There's a bunch of a small typo there. It's not significant, but I could improve the thesis readability.
Yes.
Well. I want to ask a very important question here because that's one thing which you want to reduce the power consumption and actually create a very nice eye diagram, basically, okay, because for your digital aspect. But here I want to ask one question about your analog questions because analog play a pretty important parts in your design, which actually, particularly when you get to the singular parts from your power detector, the photo detectors, then you went through the bunch of the TIF, the amplification or transfer, and so on, so on. So and also use number of the chip, the packaging there. Actually, using the So what are the PCB effects here? Because you talk briefly about the resistance and the capacitance, parasitic effects here. But can you elaborate a little bit this particular part because this could be very important for your general performance, let's say.
Yes. So I think you're referring to this first receiver. Are you referring to this first receiver, to the design one?
Okay. Yeah. Well, there's particularly, I think one of the things you talk about the PCB in your thesis. You talk about the effects, I had to go back because that's all read many days ago. That's given me a pretty strong impression because I'm an analog person. Okay, I'm the millimeter terahertz person. So I'm very sensitive to this the statement about parasitic effects there. So you can really I have to go back to your thesis.
Oh yeah, I think
it's a thesis. That's right. The written on the page. I think page 40, for example, 40. You talk about the that's page 40. Yeah.
40. Oh,
yeah.
okay.
You talk about the number of the parasitic variation at the input due to the connection to this. So, but you talk about very briefly, but you didn't. I know that's because come from the paper presentation. So I know that you don't have much detail. You can.
So in this receiver, actually, at that point when we fabricated this receiver, we didn't have access to. We were not able to wire bond the photo detector to the input of the chip. So what I had to do at that point is that I had to make the connection through a PCB. And because the package that I used was QFN80, which is a large package, and my IC was very small. It's like 1.5 millimeters by 1.5 millimeters. I had to use long bond wires. So long bond wires. So these long bond wires, I estimated the length to be 3 millimeters. And if you use the rule of thumb, like 1 nanohenry per millimeter, so I estimated that this bond wire has a parasitic capacitance of 3 nanohenries. And in addition to that, I did some research to find the package capacitance of the package which we used, which was QFN80. And I estimated that package capacitance to be 80 nanohenries, 80 femtofarads.
Okay.
So the combination between these two capacitance created a cut-off frequency. It deteriorated the signal at the input. So this is why I was limited to 12.5 gigabits per second in this receiver. So these parasitics at the input. But we were able, like in the second receiver, I managed to wire bond the photo detector array to the chip, and this has also helped me push the speed as well. So I didn't have that limitation. So yeah, and one other things to note is that RX4, I don't know, and maybe you were referring to this as well. RX4 has a deteriorated performance because when I did the layout, I didn't have enough space, so I had to place RX4 far away from the input of the chip. And this is long connection. It helped in it deteriorated the performance of this particular subreceiver. So this is how the parasitics impacted my, deteriorated my, this particular chip.
Yeah, because the they use long wire, the bonding wires. It's then eventually you create a kind of the low pass circuits. Actually,
yes.
You have the capacitive path, the inductive wire there. So you have pretty long. So this could be used to determine the interconnect efficiency here. So that's one of the things which is. On top of that, because you talk about the receiver here, of course, if you look at the input output, you have the digital bits there. But in the intermediate, the circuit design, you had a number of the CMOS, the chip design here, basically all the analog parts. What's the receiver, the noise performance? I'm not talking about bit rate here. I talk about noise performance here because have you evaluated this in your print? Because this is something which I actually am missing in your thesis somehow.
Oh yeah. So I did the noise analysis I did for this receiver was because I did the noise analysis I included in my discussion in the thesis was about these RC AC. This AC coupling and its impact on the noise. But I didn't do the noise analysis reflecting to the input. I think because I felt at that point of the design, so this was missing because I think this the sensitivity was limited by how much I can make the switch or the latches switch, this analog to digital converter. So I needed to apply enough voltage, which I think was higher than the noise level, to ensure that the CML latch actually can switch. So I was limited by the swing to make the latch switch, but not by the input referred noise. But yeah, I think this is an important aspect to discuss as well.
Particularly for your the transimpedance amplification here. So that's the first stage, and also you look into what's the impact on the the subsequent stage here. So I thought maybe you should give a little bit information on that usually.
Sure. Yeah. I did that in the second receiver, but not for the first one.
Okay.
I had it.
Professor Wu, do you have other question, or do you want to keep the other question
for
the second round?
Okay, I keep for the second other question on the antenna for the second one. Okay, I'll come back. Okay, so go ahead.
Okay, perfect. Thank you. Now, Professor Roberts.
Yeah. Hi. Hi, Bahar. Thanks for the excellent presentation. I think you did a great job there. There's no doubt in my mind you are a great experimentalist. There's no doubt in my mind. You have done a lot of chips. You go on the bench, you collect data, and you show the working circuits. So that part, outstanding. I do have kind of a similar concern that Professor Wu just mentioned with regards to the noise, but I'll take it at a slightly higher level. So we'll start by just looking at chapter 5, because that's really your main design that you discuss and describe in the thesis. And so if I take a higher view of what is happening here, you basically are describing your algorithm. Then you describe the theory of operation, then you do simulation, and then you show through fabrication that the results more or less conform to what you expected. There's a few little gaps in there that I see that where I would have closed the loop around that would have made that chapter really strong. So one example is you do some distortion, noise analyses, but at the end, what you have on the bench is only the bit error rate. So you never go back to show the reader, show one that the theory that you developed is correct. You're just simply leaving that up in the air. Would you agree with that assessment?
So, so what do you mean by theory? Do you mean like, is the receiver actually functioning? Because
no. The algorithm is what you're saying is the functionality, right? You're saying, oh, do this with the bits, and you'll get a result, right? Whatever the result of the algorithm is.
Yes.
Now, throughout the chapter, then you describe non-idealities and the impact on that algorithm, right?
Yes.
That's what you do in chapter 5. Then you go and then you fabricate, and basically all you confirm is the bit error rate.
Yes.
So all the theory that you presented, you never validated that theory is correct.
Yeah.
And has any real validity there. It's just, this is what I think, and hey, I got a bit error rate, so therefore what? So what would you conclude?
So actually, so to me, like the verification that the chip actually works is that the receiver is doing the decoding. So what I apply is not what I get at the output. It's not an amplifier. So I'm playing an encoded pattern, and on the other side, I'm getting the decoded pattern, which I expect. So
yeah, so I'm not arguing about that. That's what I'm saying. You're doing the algorithm. You're getting the algorithm. It's about the theory that you present in the simulation, and it relates to Professor Wu's statement about the noise analysis. You spend time theoretically describing a noise model, but you never validate it, and that's true for the distortion and so forth, right?
Yeah.
So what would you do to investigate? Like, in other words, a bit error rate is one thing, but what would you do to dig in and try to understand the limits of your design from the noise distortion point of view?
Yeah, so like, I mean, this is an interesting comment. So what can be done is actually just simulate or do a very expensive design where you try different receiver, for example, with different input parasitic capacitance. to study that. So you look at the bit error rate for different receivers with different input capacitance. But that was not really feasible for us. Like, for example, in this case, as you can see here, I'm doing the signal to noise ratio versus the input capacitance. And ideally for me, because I want to compete, I have to present a design with good numbers. I need to decrease this as much as possible. So my goal was to design something that has the best signal to noise ratio. So that's what I did. But if I want to validate this more, so then I would have to have more than one variation where I put an extra capacitance as the input to validate, for example, this aspect, the signal to noise ratio aspect. So this is what can be done, like creating variations. That's what could be done to validate this experimentally. But from like what I can do here, or like what feasible for me to do is do simulations, simulate, and then look at the output, and then look at simulations. Make sure that my analytical model falls with simulation. I think I did that as well. So here I have an analytical model and the simulation plot. So I had an analytical model in MATLAB, and then I had some circuit in Cadence. And I ensured, and we actually got the same comment from one of the reviewers. He's saying you're only putting the comments, but you're not validating them experimentally, these simulations, which I did here. So I tried to do as much as I can with what's available to me, which is simulation tools. But in terms of measurements, it's not possible to push it more, like feasibly, like economically.
Okay. So rather than repeat, I have questions. You see, so several questions. Okay, so I'm going to come back to that statement that you just made, the bunch of statements, because it relates to a bigger question, and I'll come back to that. But before I do that, the reason I jumped into chapter 5 first, so I jump back now to chapter 3 and 4, and I ask the same question. I say, okay, algorithm, theory of operation, simulation, fabrication, validation. I don't see any theory of operation. I don't even think I see simulation in those chapters, but I see fabrication and some data. So that left me wondering, like, why? Why was it like that?
Which, like this architecture?
Okay, let's start with chapter 3. Just go to chapter 3. I'm glancing through it and I'm saying where I see the algorithm being described. Yeah. Yes. I see a chip and the setup basically of the PCB and whatnot. And then, okay, you got some simulation results of just the transimpedance gain.
Yes.
And then you just do some experimental.
Yeah, actually,
so I'm wondering, where's the body?
Actually, like I did all of that, like when, but it's not in the thesis. But when I designed this chip, I had everything. Like I had the 4 receivers, and then we did simulations. We had a pattern, and then I had clock phases. I was monitoring all 4 outputs and checking them on simulations. So we had that, but it's missing. I guess it's missing from the from.
Yeah, and I would say so. My comment is it should be there to balance out the otherwise, what does the chapter confirm? And I'm going to get back to that question. So then I go to chapter 4. I have the same. We don't have to spend time on that again. But chapter 4, I found the same. I have the same criticism. I see algorithms. I see a chip, and I see some data. Okay, so my final question of this round goes to the bigger question, okay? And the bigger question, I got stuck right from the beginning. I always do this when I read a thesis. I look for the claims of the thesis, but I look at it from a point of view of a scientific hypothesis. So I say, okay, what is the student doing? So what do they claim they're going to do? And then did they do it?
Yes.
So I look at your claims. So let's go at your claims, thesis objectives. In your claims, you talk about, I'm going to build something. And then you, of course, at the end, show that you built something. But I look at it and say, well, what's the scientific value? What did you do?
Yes.
What are you claiming is novel, unique, important?
Yes.
And therefore, do you show that that's it? Now, I know in some of your stuff, it's clearly, I'm not challenging the fact that you did do some novel things. What I'm challenging you on is you're not stating it very clearly.
Yes.
Okay. So let's just go on page 6 of your thesis. So here, we'll go with the first one. 2 optical receivers with conventional front ends that leverage optical delay lines were developed. All right. So you can read the rest of it as well. I won't. What are you claiming for your thesis that you're demonstrating here that's important and of scientific value?
So what I was aiming to demonstrate is that it's actually feasible, and we can leverage silicon photonics to reduce power consumption or to replace blocks of the circuit. And this is what I demonstrate.
You're stating the obvious that's there, right?
Yes.
I'm saying something more than that. I'm saying that's my problem is you're not stating it in a scientific way.
Yeah.
So what are you doing in this thesis? And you're going to prove that it's true, I hope. That's always the objective, right? You make a hypothesis, and then you demonstrate, and then you prove that it's true. So what are you proving here?
Yeah. So because I have many topics, I'm trying to prove.
Just stay on that one question. See, here's the issue, right? You did not design that circuit, or at least the architecture. That's my understanding. That's not what you're putting forth, a new design. My understanding from what I read is you built the prototype that validates the design.
Yeah.
Is that a correct read?
So in some of the cases, yes, like the first
they are just that one point. Just stay on one point. I'm not talking about the other ones. Just this one.
Yes, which is like there are already existing architecture. I'm just validating, I'm answering that it's true in some cases that I'm validating an existing idea, but I'm also coming up with my own idea. For example,
I'm not questioning that. I'm questioning the claim that you're making there. I'm saying it confused me because when I read it, I look through the thesis for the hypothesis and the conclusions of the hypothesis. So here you're saying, you're making the argument that these are novel techniques, but is that your hypothesis of your thesis? That what you're demonstrating is a new design, never been done before, and I'm going to validate that design through my experiment.
Yes.
For the first point that you have.
Yes, but it's not. Yeah, this was not demonstrated before on the bench. Like it was not built before. So I came and built it.
Okay, yeah, exactly. And that's what I'm trying to get across to you is that you need to be clear about what your statement is of your scientific value. You can't say you're proposing a new optical receiver because you didn't do that. What you did was validate an idea that has never been validated before.
I mean, for example, in the second point, it's actually novel. This was not demonstrated before.
No, I'm talking about the first point, right? I haven't moved on to the other points. I'm talking about the first point.
So this one, I'm talking about this point. This point?
Which point are you? I don't know what you're pointing to. I see only your PowerPoint.
Maybe.
Okay, so I'm going to stop sharing and do a new share. So I'm talking about this point.
Yeah. No. The first point. The first point.
Okay.
That one. I'm talking about that one.
So on this one, yes. So there was already an existing silicon photonics concept, and my role was to actually just demonstrate the IC side on this.
Yeah. Point. So now that we're obviously crossing ourselves with points. So now that you know it's this point, okay. Yes. So what I'm asking is, what is the scientific statement that you would make to say what your thesis is doing? You can't say you designed it and want to develop it because you did, right? Yes. So what is it that you're doing? And because I got a hint that I got to move on, I have problems with the structure of your claims. They are not tight in a scientific manner. And so it leads too much ambiguity. And I think you could do a better job. And that's really what it comes down to. You can tighten up your presentation, state very clearly what you're doing, and that way others will know exactly what you have done so that you can go forward on that. Making them too loose is always a bad thing. Okay, I'll move on.
Thank you, Professor Roberts. We'll move on and we'll come back to you if you have other point in the second round. Now, Professor Weisman.
All right. Hello, Baha. Thank you for your presentation. I hope you can hear me.
Yeah.
It was very interesting. A lot of experimental validation. I would like to first agree, Professor Roberts. the points made. I think I also felt that while reading your thesis, I felt that it is not, 100% clear what is the scientific contribution of some of the parts. I hope to get that from the presentation, but I think it's still not 100% clear, and you could do a better job there. I will try to go, as this is not entirely my area of expertise, I'll try to go a bit higher level on some of the stuff, but then we'll dive into other stuff. I would also like to support Professor Wu's comment on proofreading the thesis. I think it needs like a couple of go-overs. First, I want to talk about motivation, right? So you talk about a lot of data is transferred among data centers. My question is, and it's a question of motivation and application. How much data? What is the application of the transceivers that you propose? Is this going to be at the PCB level? Is this going to be at the package level? Maybe we'll see optical communication on chip soon, or
Yeah.
how does the motivation tie to the application?
Yes. So, like my research work is focused on like within the package actually. So that's my goal is to design receivers that go in the package, like small receivers that go in the package, and the target applications is intra data center communication. So if we have a data center and then we have mainframes communicating with each other, so that's the goal of this thesis. So that's the target goal, is to develop receivers for these intra.
Okay, but do we have integrated circuits that generate data at the speeds of these receivers and transceivers? Do we have enough data to feed into this?
We do actually, and there's so much data, we actually try to push them as much as we can. I mean, there are data available that we need to transfer, and this comes from the applications like streaming applications, or like many applications that or cloud computing. So there's requires to move a lot of data.
Okay.
So what we need is
how about the ability of the chip to receive such amount of data I/O wise?
I think it can be done. Like here, we demonstrated 20 gigabits per second, which is high. We also need actually to do higher. So the chip is like functionally, it can receive data. So
so my question is, yes, you have a very high speed, but basically effectively replacing SerDes or trying to replace SerDes, right?
Yes.
You're taking a lot of parallel data, you're serializing it, and then you deserialize it at the end, right? Now, my question is whether there's enough I/O on the digital side or on the IC side, CMOS side, to receive all of the data that you're deserializing.
Yeah.
And I can tell you that there are significant limitations in integrated circuits, I/Os, bumps, C4s, and so on, that make it actually very difficult to receive such an amount of data.
Yes.
So
like the receiver does deserialization, but I guess we would need, like depending on the intended application, we need to have maybe a SerDes to like demultiplex as needed, as required by the digital part or the next stages. Yeah, so that would be needed. But I mean, what I've seen is that most people designing these chips, they target demultiplex by 4. So at 20 gigabits per second, they give 5 gigabits per second output. So that was I've seen from research in this field.
Okay, fine. So just one more note on motivation before I move on is, have you looked at the comparison of this with SerDes?
And this receiver, I mean, these.
Your optical communication scheme altogether at a higher level, right? Your receivers and so on, as compared to SerDes. You have micro SerDes today that go on package, maybe on chip even. Have you looked at the comparison?
I compared to other similar receivers, like optical receivers, but not with SerDes. Like I haven't looked at this comparison between SerDes and optical receivers. No, I haven't done that. But what I compared is like I did a significant comparison to other receivers.
I saw these tables. I read that. That's not, I mean, we could talk about that in a minute, but I suggest looking at SerDes as well. I do know that SerDes consume a lot of power, but the question is, how does this compare? I think it's interesting, right? Before you motivate optical communication, you should be able to compare to other stuff.
Okay.
So at the higher level, just for someone that hasn't been into optics a lot, could you explain to me on a say I have a PC board, right? And this PC board is, it has all sorts of integrated circuits or packaged, chips, whatever. So the receivers that you propose, they sit on the package of a certain ASIC, right? That's what I understand.
Yes.
And therefore, the external communication is optical, correct?
Yes.
Is that optical communication goes on the PC board?
It's like it could be on the PC board, like using waveguides. And this is on the chip. This is a possible application. It's also could be a fiber cable that goes from one end of the data center to another end of the data center. So it could be both. It could be a waveguide, a simple waveguide that carries the optical signal, or it
so
could
waveguide on the PC board.
And so we would need another chip for this communication. We need a photonics chip also on the PC board to carry the optical light, to carry the light.
Exactly. So this you lead exactly to my question in terms of trade-offs. Okay, at the end of the day, we care about right, power, latency, and so on. Yes. And the question is whether at the system level, when you zoom out, how will this compare to the systems that we have today? And there's other integration approaches, right, where people are looking at very extensively right now with smaller chips and everything is tied together. Sometimes no package at all, and so on and so forth. So the question is how that looks, and I suggest looking at that.
So actually, I think like this is kind of being done widely. So what we're doing now is being done widely. So we're just trying to kind of improve.
Well, this I'm not entirely sure. It's a good statement, but generally speaking, the fact that it's being done widely not necessarily means it's good. Not to say it isn't. I'm just, generally speaking, that could be that case. And you typically want to not just improve on something that is done widely, but kind of break through, especially when you're, where you are right now. Anyway, let's move on. I'm not sure how I'm doing in time, but I'm guessing
Thank you.
Maybe one more question if you have.
One more question. Okay, I have a lot of questions.
Okay.
So. Okay. Let me see 1 second here. Yeah, so I'll go a detailed question. Then the second round I'll ask other. On page 18 of your thesis, you talk about the comparison of cost comparison between an AMF chip and a TSMC chip.
Yeah.
And you claim that the AMF is low cost as compared to the TSMC chip. I think this is I don't know. I was reading this and it was a bit of a unclear statement. Where what is on the TSMC chip? What is on the AMF chip? What are the functionalities that you compare here? This cost metric is. What are the nodes?
So what we're discussing is that, say we have a component that we can put here or there, like we can put it on the silicon photonic chip or we put it on the IC side. It's because the cost of the photonic chip just has photonic components. But if we can build it, so this is part of the thesis work. If we can have components built on it, such as inductors, capacitors, then because the cost is very low, it makes more sense to put it on the photonic side rather than the IC side, which of course is used to implement like electronic circuits. So it makes more sense to put it on because of the cost difference. So this is because
Okay, I understand your comment. I have more questions on this, but I guess I'll keep it for round number 2. Anyway, thank you for now.
Thanks so much.
Thank you, Professor Weissman. Now, Professor Liboiron de Douceur was going to ask the question of the external examiner.
Yes, all right. I'll give the question. So the external examiner was Anthony Chan Carusoni from the University of Toronto. You will get the report. There are 7 questions in total, so I think you triggered his interest. His evaluation was overall good, and you'll see the criteria. It's excellent, top 10%, and 3 criteria got very good. So overall, he comments on this is a large body of work with impressive validation, experimental validation. The thesis is well written, and the work has potential for real impact. So the first question, I'm going to read the intro to the question to give you his state of mind. I am surprised to see the power savings claimed by reducing the number of clock phases required. The total load on the clock network is relatively unchanged. In fact, the total clock load may even be increased since optical demultiplexing requires multiple input pads, which require a large chip layout and hence larger clock distribution networks. Moreover, the proposed techniques still require precise alignment of a single clock phase, thus a phase shifter rotator is still required. I suppose the premise is that savings are obtained by eliminating the need for multi-phase generation. However, most of the method for precise clock phase alignment in high-speed wireline receivers involve the use of a phase interpolator, as in figure 9.1. Maybe you can show that figure just for the context of that question in your thesis. We see your PowerPoint slides. I don't know if you can change that. Okay, so which implies a generation of multiple clock phases anyway. So although I can still imagine some small savings, I was surprised to see the 20 to 35% power savings claim in the thesis. Can you clarify more precisely how this power savings arises?
So the load is actually the same. The load does not change. The clock load does not really change. It's very similar. So in these receivers, the load is exactly the same because we still have the same number of latches. So we have 4 latches in conventional system, and we still have 4 latches in the proposed system. So the conventional system and the proposed system, they have the same load in terms of load. Now, the power saving comes from because in many of the receivers, like we've seen, what's ignored is the clock phase generation circuit, which could be power hungry, and also at high speeds we need also duty cycle correction circuits and quadrature correction circuits as well, which we also should take into account when we look at the power generation circuit, the clock generation circuits. So this is where the power saving comes from. So it's still the same load in terms of the receiver, but we're removing circuits. So that's why we get the power saving. And it's possible to, in terms of, as Professor Carusoni mentioned, it's possible to have more compact layout by having, the thing is, when we designed this chip, we had the large layout because of the photo detector array. But we can have monolithic chips where the layout is smaller, and then we do not need to have this complex distribution network, but we still maintain the clock phase. We still maintain the power saving from the clock phase generation circuits because we remove them. So I think it's possible, like there is some power saving. And also in terms of the phase interpolator, this saving comes from so we usually use an oscillator to generate the clock phases. It's very simple to have, instead of 4 clock phases, by reducing it to 2 clock phases, as he mentioned in figure 9.1, we only need to generate 2 clock phases as opposed to 4. So yeah, so there is still power saving. And this, but it's just difficult to compare across different designs.
Right, right. So maybe, I mean, he's wondering if you could justify your claim by comparing works in the literature and instead sketch of a receiver architecture, including the clocking circuitry required for multiple clock phases, and compare that with, for example, figure 9.1, illustrating where the power savings come from a bit more precisely. That's question 1. Question 2. What do you think ultimately limited the overall sensitivity of your prototype receivers in the lab? In addition to thermal noise and other effects that are readily predictable, sometimes subtle interactions can limit sensitivity. For example, I would expect the latch circuitry in figure 4.6 to have significant hysteresis. Is this, I guess there's two questions. So is this something you observe in simulations? The hysteresis of the latch, oh, you just passed it.
4.6.
4.6, yeah, the latch there, did you notice hysteresis in the lab?
And
Sorry, through simulation, sorry.
Simulations. So I think that actually we noticed some, but we were able to overcome it with increasing the like with boosting the optical signal. So yeah, there might have been some here in this particular receiver, but we were able to overcome it by increasing the power slightly. I mean,
and what limited the overall sensitivity? Like ultimately, what limits it?
So the thing that really degraded the sensitivity in the for each design. So for the first design, so for this design, it was the parasitics at the input. We had a large bond pad, and then we had the bond wire, and then we had large capacitance at the input from the package. So that's what limited the sensitivity in this particular receiver.
But if you remove those, if you make those perfect, what's the next thing that would limit sensitivity?
What's the limit? I think it would be the latch switching. So we'll have to have enough signal in order to make the latch switch.
Okay, so I think that's what he's insinuating a bit in his question. So you may want to clarify that as well a bit.
Because he's saying thermal noise is is given. So
yeah. In addition to thermal noise and other effects that are really they're predictable, right? You know the pads, you know the parasitics and wires. So yeah, that part that it's not, you wouldn't expect it correctly. Okay, question 3. In the abstract, we claim that -7 dBm is the best reported sensitivity.
No.
Can you please clarify this? Even in the comparison table 4.2, there are other works with better sensitivity and higher data rate.
I think I was referring to the energy efficiency, not the sensitivity. I'm sorry if this was confusing. It's the energy efficiency. Like I've seen a lot of, I've seen -15 in terms of.
Right. So I think he's
the best reported energy efficiency. Sorry, this is the title.
That's a good catch.
Yes.
All right. Well, thank him for that. Okay, another one, and I'll keep the rest for the rest. I'm not getting scolded by the protein. So in chapter 4, you describe a TIA with a bandwidth of 24 gigahertz, which is intentionally higher than the input data rate. What ultimately limited your data rate to 17 gigabit per second? Was this really intentional? Wouldn't your result have been better in virtually every regard if you had designed for a lower TIA bandwidth?
So this reduction comes from, I think, from fabrication versus simulations. So when it's fabricated, the bandwidth was lower. So this is where it comes from. And I agree with the statement. He's suggesting that, yes, if we design for lower bandwidth, of course we'll be better. There will be less noise within the bandwidth of the system. And we can have even more gain because the gain bandwidth product is fixed, so we can have more gain. So yes, it would be better to design for lower bandwidth. So it shouldn't be higher. So in this case, it shouldn't be higher. Yes.
Right. Yeah. Okay.
Thank you, Professor Liboiron-Ledouceur. Now to Professor Bahaa.
Thank you. So I'm going to have a bit more naive questions for you because this is clearly not my area. However, so I guess, and I think actually Professor Weisman kind of alluded to that. Why 4 is kind of a magic number here? Could have you done with 2 channels, 6, 8, 18, whatever? It's a question we have. In my field, why 3 phases and not why 6 or something? Yeah. What's the magic number 4 here? Is there kind of an optimal that arises?
So it's kind of you want to have some form of demultiplexing. So because the next stages, they can't operate at high speed. So you have to have some form of multiplexing. The question is how much? 4, it seems to be kind of nice because you will have a small number of latches. You don't have that many latches, so you don't overload the clock. So it's a kind of a nice number, and quarter rate is, I mean, there are receivers that are 2 demultiplexed by 2 or even demultiplexed by 16. But what's common is 4 because of it's easy to generate. It's an even number, so it's very easy to generate with an oscillator or with a cross-coupled oscillator. So it's very easy to generate. So it seems to be common because it's just a nice number to have without overloading the circuit, without overloading the latches, without having too many latches. So yeah, that's the number 4.
Or perhaps it's just an artifact of what others have done in the past also.
Kind of, yes. It seems that this is the direction that a lot of people are taking. So for like in most of the literature, the demultiplex is done by 4.
Okay, so so you're claiming because of your approaches, you're able to save on power. But typically, whenever we do design and engineering, there's no free lunch. You know, you're gaining something at the expense of something else. So what can you perhaps summarize? You know, I know you have a lot of stuff to talk about here, probably. So what have you lost? What are you losing, or what are you are you, obviously your circuits are going to be different, so therefore what are the main losses you have to take?
So I would say the biggest loss is the sensitivity, because in these receivers we split by 4, so each sub-receiver only gets 1/4 of the power. So you're saving power consumption and clock generation, but you're also losing on sensitivity. So that's the main trade-off of this work. This trade-off between power consumption and sensitivity. So that's the thing that we lose the most. It's sensitivity.
Okay. And what about fabrication? Is fabrication more complex or more expensive for the same functionality? Can you comment on that?
So it could be more expensive in terms of so if we're doing conventional chips in conventional process, yes, it could be more expensive because we have to put the receivers far away from each other so that they can be connected to the PON pad. But if we move to something to the monolithic integration, then because the photodetector is on chip, then we can squeeze them, and then it may be a little bit less of a concern, this space. But yes, this is also another trade-off, but it's not as much as the sensitivity. So the biggest trade-off is the sensitivity.
Okay. I have perhaps a few comments more that are more aesthetic about the thesis. I would suggest that you export all your figures not in JPEG, that you export them in a vector format right away, because you see that if you start zooming in on some of your figures are actually nice and crisp because they've been generated using a vector format. But if you start zooming in on some of the pictures, you see the pixelation, and you want this document to be in the library and be there for your grandchildren to see. And so you want it to be perfect. Okay.
Sure.
So that perhaps is something to look into. And also something that kind of bugged me was your capitalization of titles across the thesis was perhaps, again, it's an artifact again of the fact that you had integrated a number of papers, and then the editorial style might have been different from paper to paper. So that's perhaps something to take into consideration. And perhaps one last question, I won't ask a question in the next round, is so if you had, let's say, 6 months to go and some money to support you, what would you do next?
So I think, like, if I had to continue on something, it would be if I had to start something new, or what I would do is...
assume you have a lab with the equipment you want, you have money to support yourself and to buy consumables. What would you do next for 6 months?
So I would try to improve upon this receiver. So this receiver, I would try to make a monolithic integrated version of this receiver. I would put it. I would monolithically integrate the photodetector with the receiver, because I think this will give a significant boost to sensitivity. And this is what, as I mentioned, this is the trade-off. So it's the sensitivity. I think I can overcome that by having a monolithic integration. So that's what I would do. If I had 6 months, this is what I would focus on.
So you'd say this is the most, so for example, if you want to give a piece of advice to your supervisor, this is what the next student should be working on.
I think it would have a huge impact, because What we're limited by all of this work is the sensitivity. So we want to get rid of that bottleneck, or we want to get rid of that trade-off. So this is how to get rid of it. Just put the photo detector right next to the receiver and get rid of all of these parasitics. And then we can have a significant boost in sensitivity. So that's what I would focus on if I had the choice.
Okay, thank you.
Thank you so much.
Thank you, Professor Bahaa. We started late, and we have time constraint to finish, and we want to make sure we have enough time to finish the oral. So we'll go second round, a little bit shorter, and we will start with Professor Wu.
Okay, great. Okay, now let's, for second round, I want to talk about a little bit your chapter 6 on these antenna aspects, chip antennas. Actually, I have serious questions about your antenna design, and because it was not very clear for me, and particularly one point that in your measurement, you put the pair of the distance between these two antennas. I think something like the 0.3, well, actually sub centimeter the distance. That's right.
Yeah.
But on the other hand, you present simulation results for your antenna gain, which actually only valid for far field.
Yes.
Okay.
Yes.
But now it's with such a distance at such frequency.
Yes.
It's not far field at all. It's
yes.
actually nothing to do with the far field. It's actually it's just the well, I would say the on-chip or on-board or on-circuits transmission. So I haven't seen any particular radiation or antenna effect there, except maybe you should have some little bit like a near field problem, whatever. Can you comment on that?
So actually, this figure we presented is just to give an idea about the performance of the antenna in the far field. But our demonstration was actually, we use the antenna as a near field coupler because this is intended for inter-chip data communication, which are usually very close with each other. So this demonstration, yes, it's in the near field, and this was our intention, is to have it something in the near field, like close to each other within the near field, and use the antennas as couplers, as kind of couplers, RF couplers, and this is what we did here. But
you create conflict inside within this chapter. You know, it's a description which are not consistent, because if you talk about the gain should be at least because it's a monopole antennas. So of course you have the metallized ground plane here. You have, so it's not really the omnidirectional, but on the other hand, it's question that this description of this antenna for far field, and in the end you don't have far field discussion afterward. And so it's not consistent. I think it should be it would be nice for you to add more description, and particularly in the near field. I will have to say something which is my own comments. Near field, you don't have definition of a gain. Okay, or near field, you don't have gain at all, the definition. So when you claim a gain in the beginning, which is only valid for far field, but in the end you use near field, which have no gain definition at all. So so that's quite a hole in your chapter here.
I'll clarify this aspect. Yeah, thank you so much.
This is if you present this chapter to antenna experts, you will have trouble. Right away, to tell you. So I will suggest you to carefully revise these portions, and maybe discuss a little bit near field aspects, which is actually very interesting. And so now, okay, let's come to this measurement results, or the S parameters. Okay, S parameters here. So these S parameters suggest that you have the simulation and measurement results, which actually agreed very well with each other. My question is this. So the structure, because it looks like you have it's just like what it looks like it's just the monopoles. It's like only one transmission line. That's right. Because if you go back to that, the structure was not very clear You know,
Uh,
to me, yeah, that's right, this one. So it looks like only one. Where's the antenna here? It looks like this.
so this is the ground plane, and this
Okay.
is kind of the structure of the antenna.
Okay, okay. So this, okay, it's kind of the well, I wouldn't say this one really looks like the monopole. Okay, the reason why I'm saying you have the well, you may say that it's like the folded monopole. Okay.
Yeah.
But actually, it's you have, because you have a strong coupling between the elements here. So
Yeah.
that's the second point, that I would say that you had to make sure this statement of monopole. What I suggest, maybe you should add a field distribution. For example, you can use HFSS to calculate the field distribution of this this surface, which antenna surface. You can tell right away that whether this is a monopole or not monopole. Okay. So which is not clear for me. So that's the so because when you discuss when in your chapter, you talk about the monopole, you talk about the ground plane effects, those things. But in the simulation didn't show any parametric analysis there. It didn't show the antenna, what are the behavior of antennas. You just show you one results. There's no any further analysis. So I feel maybe it's it's just my comments. I would say I know this is already between far field and near field, there's conflict there. I will not say anything beyond that point. But this will be just suggest you to improve this chapter.
Sure. Yeah, I try to do field simulations and show them, add them to that.
Okay. Maybe one question about this, because you in the thesis, you discussed extensively about the circuits on silicon, okay, or silicon photonics, use of silicon photonics. Now there's always a big chance on in the field that we want to integrate a 3,5 compound on silicon, okay? So create a heterogeneous integrations. Eventually we can do lots of active functions, within silicon, because silicon is not good for active functions, okay? So that's everybody know. So what have you seen any opportunity in your let's say in your work here to integrate 3,5 compound with your silicon photonics? This is general questions. I see that how you visualize your work, how those technology can be useful for you.
I mean, I think it's an interesting direction, but I really haven't looked into. So my work was mostly focused on the silicon photonics, but I haven't looked into like 3.5 and how they can be used. But I imagine, yeah, I will have to.
Because you talk about the monolithic integrations, okay?
Yes.
So because right now you use PD, Maxanda is use external, the parts.
Yes.
But if you want to make a monolithic integrations, pure photonic, silicon photonics may have difficult to achieve all the functions. Okay, so if you want to add, let's say you create a true monolithic electro-optic, transceiver or receivers. You have to consider how let's say, if you want to design Maxanda modulator and or the PD in your own photonic, for the silicon photonics. So what do you do?
And so, like so the thing that I focused on, so when I mentioned monolithic integration, is the photodetector with the antenna, which could be done on silicon photonics. But if we were to include other actives, then we'll have to take this design and put it in 3.5. So, but I mean, I haven't really looked in 3.5 technologies for this implementation in particular.
Well, this is this is important. Okay, okay. So I stop here. I know that okay.
Thank you.
So thank you.
Yeah, we have to move because we're a bit tight. So thank you, Professor Robert.
Okay. Can you go to slide 16?
Slide 16. I'll share my
Yeah,
screen.
yeah. Of the presentation, yeah. I just want to recall something you said. I just want to understand it a little bit. Okay, so if I recall correctly, in your experiment, you manually tune the delay line to line up with the clock generator.
Yes, using this.
So, yeah, using that delay. So my question to you is, when you integrate these systems, these two components into a system, would there have to be a circuit that did that adaptive tuning, if you will, to align them?
There would be, yes.
Okay, so would you then say, well, if I have to do that, would that not have to be part of the power budget?
It would need to be included in that situation, yes, but that's always the case. I mean, you'll always have to have a circuit that aligns data with the clock. Now, we're not showing it here, and most of the literature doesn't show it in these kinds of receiver, but it has to be included. So, yeah, it has to be included, but it's not particular to this technique. It's not.
Well, hold on. Is it the same? Are we talking about that it's the same so we can discount it? We have to have some, I assume, something on silicon electronics that drives across the interface through the parasitics to the chip that has the delay line.
Yes.
That's not quite the same as a circuit that's on the same substrate driving the electronics.
But you can put it here, like you can just put it on this side, you know.
Yeah, but you have to sense, right? You still have to sense.
You still have.
You have to sense you have to somehow know what the delay is, or you're just saying you're going to just look for a peak detect. Whenever it goes up to the maximum, you're aligned.
Yes. You can put it here, like you can put it on the same chip. It doesn't have to be external where it's complicated. Yeah, but you can put it on the same chip. I imagine it could be done.
Right. But my point really is to say there's a lot of pieces that you're leaving out of your budget, your power budget, that you're not accounting for, that must be part of this system.
Like what?
Well, what I just asked you about.
Yeah.
I'm just saying, is that like that's a concern, that say I've got the lowest power, but I leave out all these other components.
Yeah.
That's a strong statement. That's a very
I think it's like this has to go with the comparison I make. So I'm comparing with similar receivers with similar implementation. So most of the receivers in the literature, they don't include this circuit that aligns data with the clock. It's actually done manually in most of the literature. So I'm comparing to the similar literature on this level, which it seems that everybody is ignoring this alignment part, the clock versus data alignment. It's all being done manually. So when I claim this, I'm not claiming it in general. I'm claiming it specifically to other similar literature, which uses exactly the same technique of aligning data and the clock.
Okay, that's actually very helpful. And that would go back to my earlier point about your hypothesis. You should make that clear so that it's clear, scientifically speaking, what you are comparing to, so that we know what you're delivering, right?
Yes. Yeah, I'll revise
Okay,
this.
so yeah. I'm just going to go back. I have only one more question. I have lots of questions, but I don't think I need to keep going on them. I still have an issue with your statement about the silicon photonic process is cheaper than the microelectronic process.
Yeah.
That's really surprising to me. And so are we saying on a chip by chip basis that if I can mass produce, let's say 1 million chips of silicon photonic chips versus microelectronic chips of whatever flavor, the silicon photonic will be cheaper?
It's because silicon photonics is using like legacy CMOS processes. So they're using older.
Oh, so okay. So you can't say, if I can use legacy microelectronics, there may be some circuits that I can build in that legacy process that says this statement is not true.
Yeah. Then in that case, yes. But in the context of high speed, so we want to use. If we look at the literature in this, we find that most implementation are in using modern technologies like 28 or even better technology.
Okay.
So in that context, with high-speed receivers into account, when you take that into account, then that statement is true. But if you want to compare ancient technologies, yes, then if we compare 130 nanometers, then it's not.
Okay. So let me go back. Then I say, okay, I understand your qualification. Then I say, okay, so are we accounting for the volumes that would be produced? Are we saying that the volume of the silicon photonics IC would be equal to the volume of the microelectronic part? Because if I sell 10 times more of the electronic parts, then my cost for electronics goes down by a factor of 10.
Yeah.
So how does volume come into this? Are we saying that you're going to have exactly one chip to every, let's say on the photonic chip that matches the electronic chip?
So, and like in this statement, the assumption is 1-to-1. Like we only have one chip of this and one chip of that. So, and the comparison was based on the prices provided by CMC. So we just compared the same area, 1 millimeter by 1 millimeter compared to 1 millimeter by 1 millimeter. So that's the comparison. We didn't take into account production volume.
So then even that, so you're just talking about 1, 2, I think 30 chips being made then. It's a volume of 30. That's what CMC based their price on, 30 chips.
Oh, okay, yeah. Yeah, then that's the case.
So,
I didn't realize the production 30.
Yeah, so I mean, I'm sure the price of an advanced CMOS technology on a per chip basis is going to be a lot cheaper than what CMC provides.
Yeah.
So again, I think that's a big statement. You don't realize it. That really caught my attention as well. And you should elaborate more on that too. So that it's clear what it is you mean. Okay, I'll stop there. Thank you very much.
Okay, thank you, Professor Roberts. Now to Professor Weisband.
All right, so I'd like to put in as many questions as possible in my time. So first of all, and I think this goes to the main, result of this thesis, is I'm looking at the comparison tables of chapters 3, 4, and 5. And just as an example, let's take 5, which is page 117 on your thesis. And either I'm not getting something or other chips seem to outperform your chip, including in terms of power. So could you please explain, the main advantage of this work as compared to the other works, let's say in table 5.1. So I'm looking at 34, reference 34, for example, which is the same technology node. It's very difficult to compare, 65 node to a 28 node, but okay.
Yes.
But look at 34. What is the main advantage?
So, and this particular receiver, first of all, this receiver did not take into account clock generation at all. So this power that's reported here, 0.4 energy efficiency, it does not include clock phase generation. The clock phases in this particular receiver were generated externally and fed to the chip. So that's the first limitation.
Okay, so then how much power was that? You don't know, right?
They don't support it, yeah.
Well, then you can't compare to this, right? It's not apples to apples.
I mean, yeah, but so the problem with this kind of literature is that in low bandwidth receivers, people focus on the architecture of the receiver. They do not focus on the clock phases feeding the receiver. So this is what's available to me to compare with. So this
right,
is
but you have to understand, when you put something like this on a table, it makes you look bad. Yes, yeah. There's a little 2 there that says go look at the explanation. Yeah. But at the end of the day, it makes you look bad, right? Because
actually,
what's the advantage? And there are other chips here with also the same technology, 65, for example. 35 reference, also with a lower energy or with a better energy efficiency and lower power. So what is the claim to fame from this table?
So this, what I'm trying to say here is that, of course, I go into a detailed discussion in the thesis about each of these references and what's the differences. So it depends on, so for example, this reference also does not take into account the clock generation phase generation circuits. And there are also other comparisons. So for example, this receiver, it has DFE, it has direct feedback equalization. This can limit the speed. It could also feed noise, and there is a robustness concern about this receiver. So it's working.
Okay, which from these columns has exactly the same features as yours, or close to?
Unfortunately, so the closest one I would say is, let me see. The closest one is, yeah, it's the integrated and dump 52. So that's the closest one to my work.
Okay, and then I'm looking at that 52, right? And it has better energy efficiency, better power. But, you're going to say, well, it's in 28 nanometer, right?
Yeah, but I also have higher speed, even though it's an improved technology node. So I imagine if I move to 28, I'll be able to hit 30, and then my energy efficiency would drop, like it would be a lot lower.
Okay, so this is the sort of, so some people do, for example, extrapolation, right? They take certain nodes and they extrapolate, right? So you're at the same level, because otherwise it's very difficult for the reader, you know, to understand what the benefit is. So this goes to all the tables, you know, in chapters 3, 4, and 5, and you should definitely consider either presenting in a different way or emphasizing in bold whatever, you know, matters and so on, because it is you know, confusing. So I'd like to move on to the actually the second part of your thesis, which is the parasitics. And, you know, there was a discussion about antenna, and I also, you know, looked at that there was the near field, far field thing was throwing off completely. Also the 3.5s, so silicon is typically lossy at higher frequency, and somewhere in the antenna design, you talk about, I think, up to 60 gigahertz frequency, right?
This is 15. This
yeah, but you mentioned 60 gigahertz.
I mentioned that they remain large in size even at millimeter wave frequencies. So even if we move up to 60 gigahertz, the antenna would remain large in size, like millimeters in size.
Okay, right. So yeah, I think 3.5s should also definitely be looked at here. Quartz for antenna potentially, and so on.
Yeah.
But I really want to ask you about the parasitics. So you talk about capacitance density, and you show in the I think in the background you show a layout example. Have you compared to deep trench capacitors, for example? So I have a reference here for you, where deep trench capacitors in silicon were fabricated with a capacitance density of above 100 femtofarad per micrometer square.
I just want to see which part.
Well, there's the layout. I think it's, you have like 100 micron by 100 micron and 2 by 2, and then an MOS device or something like that.
Oh, okay. Yeah.
It's actually on page 19. Yeah, right here.
Yeah, this one.
So there's a reference from ECTC this year. You know, they show deep trench capacitors, and this is not like very new because it has been done before. Deep trenches, and they're at 100 femtofarad per micrometer square.
Okay,
right? Which is significantly higher than this. So the question is, can you beat that with you know, with your silicon photonics?
100 femtofarads per millimeter square.
Per micrometer.
Per micrometer square. 100 femtofarads per micrometer square. It's a deep trench capacitor.
Yep.
I will have to look into that. So, but here, so I think, so I'm not familiar with these deep trench capacitors. So, but would they be able to work at high speeds? So that's the question I would have when there's such.
You tell me.
Yeah, because I'm not familiar with them. So I compared MIM caps, which can be used at high speeds.
Yeah, but so I guess this is really the comment here is, you know, there's other stuff out there, right?
Yes,
and,
yes.
That is interesting.
What I compared here was just metal, using the 2 metal layers in the silicon photonics, and compare them to what the closest thing, which are MIM caps in the CMOS process. Of course, there are other capacitors such as.
That's fine, but deep trench capacitors are out there for, I don't know, 20 years. So people are using them.
I think
IBM you know, came up with this process, and they've been using it for decades now, or a couple of years.
I think the comparison here was limited to metal capacitors, so MIM caps on the both sides.
So I think
maybe one last point.
Yeah, that's exactly what I have. Last one.
Okay.
So on page 47 of the thesis, we talk about the 4 sub receivers, right? And you tell that RX4, you know, the performance is pretty low because of long connection there, limitation of layout and so on. So my question is, are long line connections is an expected phenomenon? So it can happen not necessarily because of your layout limitations, but maybe for, due to other limitations. And if yes, what would be mitigation techniques that you could use?
So from what I've seen is that long connection in the receiver, especially at the input, they are avoided. So they are made as short as possible. The POM pad is very close to the, and if there was a long connection, we'd be forced to design a transmission line in order not to lose from the signal. So that's the mitigation technique. It's just using a transmission line or a matching network to make sure that there is not a lot of losses. So, but usually it's like they maintain smaller size. So they maintain a very small, they're usually close to the POM pad.
I see. All right, thank you very much.
Thank you so
Thank
much.
you, Professor Weisman. Just to make sure we're okay with time, I think the constraint is, Professor Bahaa, you have to finish at 11:30, right?
Actually, my constraint got kind of relaxed. You might have seen me on the phone, so that was taken care of.
Ah, okay. So then we'll go
All right,
to
then.
Professor.
Before
in that case, I want to say I have to leave at 11:30.
Okay, perfect. So we'll finish by 11:30.
Yeah.
Thank you.
Yeah.
Professor Desboisron-Ladouceur.
Okay, thank you so much, everyone, for all the good questions and feedback. So I have more, and almost done. So I have 3 questions, and the first one, just did I read that one? Yeah. Okay. So in chapter 4, the impact of introducing resistor RLF, low filter, into the TIA. This is interesting. I understand that the feedback inductor LF can introduce excessive peaking in the circuit's response. However, I believe the peaking can also be mitigated by reducing the value of the inductor LF. So which do you think is preferable and why? Larger value of LF with RLF or smaller value of the inductor without the resistor RLF?
I would say, like, preferably from a noise performance point of view, we want RF to be smaller because it injects noise directly at the output. So we would want this to be smaller. So
but he's asking with respect to RLF, the one in parallel.
Yeah. So we want, so this RLF, I think it just models the quality factor of the inductor.
All right.
We want this RLF to be as small as we can. And then we want LF also to be small. If we can, if there's excessive peaking, then we need to reduce LF.
All right, so maybe there's a typo in this question. So either way, I think we should comment on the thesis, larger value of inductor with RF or smaller value of the inductor without the RF, RF, because we can't remove RLF because it's always going to be there, right? Okay, right, so maybe we clarify that. How do you envision co-packaging the layout in figure 5.27 with your CMOS receiver chip? You mentioned each of the 4 detectors can be wire bonded or flip chipped onto the receiver. Can you be more specific? What parasitics do you expect to be introduced by the co-packaging? What impact, if any, do you think the parasitics may have on the receiver's performance? Figure 5.27, yeah, that one.
So I think lots of what people have been doing in this kind of research, they would put the IC chip on top of the silicon photonics chip. So they would feed the chip from this side, and then they would put the IC chip here. I don't know if you can see my mouse.
Yeah.
And then there will be like transmission lines or connections to the IC chip, which is placed on top of the silicon photonics structure. So the parasitics come from this connection. The capacitance and the line that's used to connect the photonics chip to the IC chip. So these will have to be taken into account when final integration.
Okay, so we can also clarify that in the thesis. Last question. Passive structures, referring to your passive structures on silicon photonics, are subject to process and temperature variations. Thus, on CMOS chips, passive structures are generally made tunable to allow for calibration. Increasingly, digital tunability is used to allow for digital calibration under the control of firmware. In any case, MOSFETs are used as switches or tunable elements. How do you envision tuning passive structures on silicon photonic dies where MOSFETs may not be available? Or do you believe they must be designed to be robust across process and temperature variations?
I think it's a combination of both. Like we have to think about robustness when we design the silicon photonics chip. So we have to take into account like how much variation there could be, but there is also should be if it's we of course we can't always guarantee it's going to be correctly working or it's within what we expect. So there should be some kind of feedback to force to correct the silicon photonics, any variations in the silicon photonics, or to compensate for it from on the IC side, like expect like a delay line, for example, to compensate for the optical variations in the optical delay. So it's both. I think. Like it can't. There is no right answer. It has to be both.
Okay. Okay. Good. Good. Very good. That's all for the question. And I just want to say it was great supervising you throughout those years. So very good work. Thank you, Baha.
Thank you. Now to Professor Bouffard.
I have no further questions.
Okay. I think for sake of time, we will, unless there's burning question that someone wants to absolutely ask, I think we will go in deliberation mode. So Cheryl, I think thanks a lot for answering all these questions, Baha. And we will, I think, move in the deliberation